I think we can go ahead and get started now. Thank you, everyone, for coming today to the symposium on word problem interventions. And so I would like to introduce Sarah Powell and hand it over to her now.
All right, thank you. Good morning or good afternoon, everyone. Today we're going to talk about going beyond the basics of word problem intervention, and Lynn and I are going to talk about essential components of word problem intervention. So to introduce ourselves, my name is Sarah Powell. I'm an associate professor at the University of Texas at Austin, and I'm joined this morning by one of my favorite colleagues. Lynn, would you like to introduce yourself?
Sure. I'm Lynn Fuchs at Vanderbilt University and the American Institutes for Research. What you see over in the next picture is Sarah, Erica Lemke, and myself while we were in Bruges.
Yeah, so we present our stuffy university pictures, but also our fun pictures when we're out having fun and mostly talking about fun stuff, including math. So we're really excited to be here this morning to talk to you about word problem solving. So before we get into sharing some of the interesting things we've been working on in our different research programs, we thought it would be interesting to start today thinking about how do students solve word problems. So I'm going to show two different word problems, and we administered these measures to third grade students who were experiencing difficulty with math. And we randomly selected 15 students' work to show you this morning. And these are students who did not receive word problem intervention. So I think it gives a really good snapshot of what are elementary students doing in terms of setting up and solving word problems. So this will be the first problem that we look at. If you want to read the problem and figure out how you would solve the problem, take a few seconds to do that. And then we'll show you how students respond to this problem. So here's one student's work. This student wrote 20 or 26. We're not really clear on what they wrote there. And we're also not really sure what their strategy was for solving this problem. This student wrote 43. That probably does not go along with your answer to this word problem. And we're not, again, sure exactly what this student did. You will see as we look at the student work that we did encourage students to circle their answers. So that's why you see a lot of that. That helps us when we're scoring this to understand what the student was how the student was trying to answer. This student here had some strategies where they underlined important information. They also rewrote one of the names from the problem and then erased it, but we did not see the student solve this problem. The student repeated information from the word problem. So they started to kind of say like, oh, I know I probably need this 96, but then they didn't do anything beyond that. This student wrote 95, which is close to 96, and used these tick marks to try to do some calculation. I kind of hypothesize they're trying to subtract 25 there, but do notice with their strategy here, with their I guess their tick marks is what I'll call them. The groupings are not the same. So we've got a pretty interesting strategy that this student is trying to use. And then we get to students that are going to take the two numbers from this problem, and very commonly they're going to add these numbers together. So this student does that. This student does that. Notice how they checked their work. So they showed us that they did that. And I'll just put up a bunch of these, is that this is a very common strategy for these students. Nice things about this work is that these students are regrouping. So they are doing the computation well, but we can see that they don't understand the underlying construct of this problem. This student also added, I thought this was interesting work where they're circling important information and underlining the question. But again, they're adding 96 plus 25, which is a pretty common go-to strategy for students when they're solving word problems in the elementary grades. And then of the 15 students' work that we'll show you today, these two students did solve the problem correct. Now, if we look at this problem here, this is a different type of problem, and it involves a graph, which I think you're going to see causes a lot of complication when it comes to word problem solving. So take a second to read this problem and figure out how you would solve this problem. All right, so hopefully you cued into comparing math to writing. So let's see what our students did. Here's our student that used a tick mark strategy. I think they added all of the math, reading, science, and writing together. We would have to have conversations with students to really understand their strategies, but that seems to be what this student was trying to do. This student did some comparison and then knows about percentages, which is really interesting at 3rd grade. And they chose 8% more than reading. So here you can see that they're not focused on math and writing, but probably math and reading. This student repeated information from the problem, and like several of our students today, that understanding that 13 students chose writing was very difficult for some of our students. This student just repeated that 22 students chose math. This student said 22 chose math and 14 students chose writing, and lots of cute hearts there to show that they must love doing this problem. This student repeated information from the word problem. The students chose that they love more math because I think it's like 22 chose math, or they're trying to say something like that. Here we have a student that added 14 plus 13. So here we can see that they're adding reading plus writing. This student added math plus reading, or actually I think they added math plus writing. Notice in the writing column how they didn't like that it was in between 12 and 14. So they just colored that in to show 14. Yeah, it's so creative. I don't like that number. I'm just going to change it. This student now adds 24 plus 13. So an incorrect interpretation of how many students chose math. This student now is 22 plus 12. So we're getting someplace, but notice all of these students are adding right now. So that's not going to help us solve this problem correct. Here we now have a student who identified the correct numbers, 22 plus 13. But still not solving the problem correct. And then this student does compare 22 minus 15. So now we're getting someplace, but the numbers are not correct. 22 minus 12. So now they are comparing, but they're comparing the incorrect amounts. And then this student does 22 minus 14. And I'm sure you're like, Sarah, come on, when are we going to get to the correct response? And so of these 15 students, 1 student solved this problem correct. So there's what you can see here is that word problem solving is very difficult for students. There's a lot of reasons that word problem solving is difficult. Sometimes it's identifying the important information. Many times it's the interpretation of the problem. And so what Lynn and I are going to talk to you about today is that word problem intervention is key. So to help these students be successful with setting up and solving these fairly simple and straightforward problems, word problem intervention is necessary. And so the word problem intervention that we're going to talk to you about, Lynn's going to talk about a version and I'm going to talk about a version, but both of these programs revolve around a program that we call Pirate Math. And in Pirate Math, students do 2 things. First, they run through the word problem. So they read the problem, they underline important information, and then they name the problem type. And so today we'll be focusing on 3 problem types. Some people call these schemas. We'll talk about the total problem type, which some people call combine. We'll talk about difference problem type, which some people call compare. And we'll talk about the change problem type as well. And in a total problem, parts are put together for a total. In a difference problem, amounts are compared for a difference. And in a change problem, one amount increases or decreases. So you'll see Lynn talk about these problem types, and then I will talk about these problem types. But how we are helping students set up and solve these problems, we are taking some different approaches to really get at what are some of the real essential components of word problem intervention that's going to help students be successful with word problem solving. So our focus today is these 2 innovations that we've done in some recent randomized control trials that Lynn has run with her research team in Nashville, Tennessee, and that I've run with my research team in Austin, Texas. So Lynn's going to first talk about language instruction within word problem intervention. So Lynn, I'll go ahead and turn it over to you.
Okay, you can advance to the next slide, sir. So this is the title of the study, Embedding Language Comprehension Instruction Within Word Problem Intervention. And you can see who the main contributors to this study were. And I want to make sure to note that the study was funded by the National Institute of Child Health and Human Development. So why we focused on language comprehension when we're trying to improve word problem solving? Well, word problem solving is often viewed as an interaction between language comprehension processes and math problem solving strategies. But when faulty problem solving is computationally modeled using math problem solving errors versus language comprehension errors, the correct word problem representation actually depends more on language comprehension than on math problem solving. And when we change wording in only minor ways, that dramatically changes the accuracy of students' word problem solving. Now, in schools, many teachers assume that students have the language comprehension for understanding word problem statements and to build word problem models. But for at-risk children, students who are struggling with math and may develop math learning disabilities, this assumption is often shaky. And so we were exploring the role of language comprehension in word problem solving and seeing what happened if we added a component to the Pirate Math intervention that focused on language comprehension. So some people wonder, well, why don't we just put these kids in language therapy? And that is a reasonable question. But the research mostly conducted in reading shows that although language therapy will improve oral language comprehension, transfer to academic performance is limited. And so this may be especially true with the kinds of learners that we're concerned about here, because students who are at risk for math learning disabilities or with math learning disabilities typically have an inadequate foundation of academic skill. So if you're teaching language in the absence of any math, it's hard for students' math problem solving to improve. And these students also experience substantial challenges with transfer generally. And so this argues for embedding the language comprehension instruction in the context of the direct skills word problem intervention. So as Sarah was telling you, I'll give you a little bit of review or a little bit more background information on what we're doing when we do schema-based intervention, and Sarah does similar things in the intervention she's going to talk about. We role play with the student. The mathematical, we begin with an intact story, so no missing information for the students to find. And we focus on an explanation and experience with the central mathematical event associated with that word problem type. And we use concrete objects, and we use the children's and the tutors' names. And what we do is we gradually move from direct experience with that mathematical event to different kinds of representations. So we move to a visual schematic of what that problem type is about, into which story quantities can be inserted to illustrate the connection between the quantities for that mathematical event. We quickly move to introducing a hand gesture. So for the combine or total problem type, we have two quantities that we move together to form a total. That's an example of a hand gesture to quickly remind students of what the mathematical central event is about. And the tutor can quickly use the hand gesture instructionally to review the problem type. And the main representation we use is the problem type sentence. So for total problem, that was one of the problems Sarah showed you, where two parts are being combined to form a total. Part 1 plus part 2 equals the total. P1 plus P2 equals T. For the difference problem type, the bigger number minus the smaller number equals the difference. B minus S equals D. And for the change problem type, the starting amount plus or minus the change amount equals the ending amount. And once we work on that with intact stories, we then move to problems which have missing quantities, but we use the same sequence of experiences, role playing, and then the different representations with the schematic, hand gesture, and the problem type sentence. Then we teach them step-by-step strategies for building word problem models and solving the problems. So you saw the run mnemonic we use, where they read the problem or they're listening to the problem while they're reading. They underline the word that indicates what the problem is mostly about while they're crossing out irrelevant information, and they name the problem type. Then they write that problem type's sentence. They enter relevant quantities from the problem statement into that sentence structure, and they cross out any extra numbers that are in the problem, and then they solve the missing quantity. So in this next slide, this is a first grade child solving a total problem. 4 girls and 3 boys are playing on the swings. They swing for 10 minutes. How many children are playing on the swings in all? That's a very typical word problem. The child reads it, does the run procedure, reads it, names the problem, underlines what the problem is mostly about. You see children is underlined here. Names the problem type total and writes T to help her remember that this is a total problem. Writes the associated number problem type sentence, enters the relevant quantities from the problem into a number sentence that is structured like the total numbers problem type sentence, crosses out 10 because that is an extra number, and then solves for the missing quantity and writes the label. So we had one condition in this study, which was schema instruction on word problems, where we taught, combine, compare, and change problems. But in the second condition, we included embedded instruction on word problem vocabulary and language constructions. So for combine or total problems, we taught joining words like all together and in all. We taught superordinate categories, which are common within total problems, where you might have dogs and cats, but then the question asks you for the number of animals. You saw that in the preceding problem with boys and girls, but then the problem asked for children. And for compare problems, words like more, fewer, than, and ER words, we taught the idea that not all ER words are compare words. There's bigger, which is a compare word, but then there's teacher, and there are other kinds of ER words. You have to think about the word that's in that problem. Change problems, which include cause-effect conjunctions like then or because. Implicit quantity change verbs like cost and ate, which have to do with reductions in the quantity versus found, which would be an increase. Time passage kind of phrases, which are often in change problems, and confusing cross problem type constructions. A lot of our children don't hear the difference between the words than and then, which have very different meanings when you're dealing with quantities They're very important, and a lot of our children need explicit instruction on this. So you get a sense of the kinds of words and language that needs to be taught and understood in some children. A lot of children come to school with all this vocabulary and all this language understanding. And if children don't already possess this kind of language knowledge, then they're at a disadvantage within the context of word problem instruction. So I want to be sure to help people understand that it would be easy to think that what we're doing is teaching keywords. We are not. We instead explicitly teach children that searching for keywords and numbers without reading the problem and without figuring out the problem type often gives you the wrong answer. And we give them illustrations of why that's the case. And when you think about it, we had a total problem that Sarah began with today, that the one about the paper cranes. We had, I think there was the word altogether in that problem. If you use that as a keyword, you're going to add, but if one of the parts is what's missing in a total problem, then you subtract. So you have to read the problem and understand the gist of what is happening in that brief story in order to know what problem type it is, and further whether you would add or subtract to solve the problem. So let's go to the next slide. So in this study that I'm talking about, we defined risk as low arithmetic and math concepts and applications. We conducted the study at first grade. So children who entered the study had poor arithmetic and concepts and applications at the start of the year. We randomly assigned 400 children to 4 conditions. There were 391 after attrition. So there was schema-based word problem solving intervention without the language component. There was the word problem with the language component. Our third condition, also developed and taught by the researchers, was number knowledge intervention. What we wanted to do is, with that number knowledge intervention condition, was to answer this question: is transfer from number knowledge and arithmetic to word problems sufficient to support word problem outcomes? Do we really need to have an explicit emphasis on word problem solving strategies? And then we had a control group, which was the normal school program. So each of the 3 top conditions there lasted 15 weeks, 3 sessions per week, 30 minutes per session. So we controlled for time. And importantly, all of those 3 conditions included 5 minutes of speeded strategic arithmetic practice, because we wanted to be testing not whether kids could solve problems because they knew or didn't know arithmetic. We wanted to make sure that all kids in those 3 conditions had good arithmetic skill. What we wanted to know was whether they could solve word problems. You see here that, in fact, the children in the 3 active conditions had comparable arithmetic performance. And in all those 3 conditions, it was stronger than the control group with moderate to strong effect sizes. But on the word problem outcome, only the 2 word problem conditions performed better than control, and the number knowledge condition did not. And there you see that the number knowledge versus control group effect size was 0.09. You see that for both word problem conditions, the effect size was large. But what you also see is that the word problem solving with language condition performed stronger than the word problem without language condition, with an effect size of about half a standard deviation. And we also had a word problem language outcome. And there you see that only the word problem condition with language performed better than control. And all three other conditions, word problem without language, number knowledge, and control, were all comparable. And the effect size, comparing the two word problem conditions, was 0.4. So we asked whether word problem language mediates condition effects on the word problem outcomes. So if you look at the bottom panel, what you see is if we're looking at word problem language versus control, that contrast produces a significant difference on the word problem outcome. So that path is significant, a significant direct path. But we also have a significant indirect effect because that contrast also has a significant effect on word problem language. And word problem language has a significant relation to word problem solving. When we multiply these two significant paths against each other, it's significant, which tells us that part of the effect, the direct effect that we get, the total effect that we get on word problem solving, is attributable to this indirect path where the word problem condition with language is improving language. And for every unit of language improvement, we see an additional improvement on word problem solving. And so that is the mediation effect. We get that same mediation effect when we're contrasting word problem with language versus word problem without language. So that also mediates the effect on the word problem outcome. Next slide. So implications for intervention on word problem solving. Number knowledge intervention does not provide added value over control, despite that number knowledge intervention does improve arithmetic skill. So transfer from arithmetic to word problem solving is not sufficient to support word problem development. So explicit word problem instruction is required for at-risk learners. On word problem solving, embedding language instruction into validated schema word problem intervention offers added value over word problem intervention alone. And so we conclude that teachers should incorporate language instruction within their word problem intervention. So I'm going to pass the baton over to Sarah.
Awesome. All right, thank you so much, Lynn. So Lynn focused on language instruction within word problem intervention. And so I'm now going to focus on another piece which we saw being used in Lynn's project, and that is a focus on equations that are used to represent different types of word problems and some of the supports that are important to embed with students in order to solve those equations well. So we'll talk about using equations to represent different types of word problems. Just as Lynn talked about, all of this work comes from the original program that she and I and our colleague Pamela and others developed at Vanderbilt University called Pirate Math. And with this project, which is funded by the Institute of Education Sciences, we took Pirate Math and we embedded this equation quest activity within Pirate Math. And so we call this program Pirate Math Equation Quest. In Pirate Math Equation Quest, just as with Lynn's project with Pirate Math at first grade, students learned to run the problem. And so they would read the problem, underline that label, cross out irrelevant information, and then name the problem type. And in this program that I'll show you today, students worked on 3 of the word problem schemas. We have another variation at 3rd grade that worked on 4 word problem schemas. And we're now working at 4th grade where we're looking at 5 of the most common word problem schemas in the elementary grades. But we'll talk about these today. So I just want to review that in total problems, students have parts that are put together for a total. In difference problem, students have amounts that they compare for a difference. And in change problem, students have one amount that increases or decreases. So I want to show you some of the different word problems that we set up and solve with students, and then talk about this role of an equation to help students understand the structure of this word problem, as well as how to set up and solve this word problem. So with this problem here, James rode his bike 14 miles Saturday, then he rode 23 miles on Sunday. How many miles did James ride his bike? We would help students think about this problem as a change problem because we started riding some miles and then he rode some more miles. So here students would use an equation, perhaps 14 plus 23 equals question mark. You see, we are going to replace that question mark with a variable pretty soon, but initially we start off with just like, what is the unknown? We're not sure. But it's this equation here that represents the structure of this word problem. So we have the start amount and we see this change. There's an increase in how many miles James rode his bike. And so our job is to figure out how many miles he rode his bike across those 2 days. That's an example of a change problem. This would be an example of a total problem here. Here we're asked to figure out how much Carter, Truman, and Lincoln spent all together. So we're putting all of these amounts together. Many total problems don't involve just 2 parts, but many total problems might have 3 or 4 parts. So this is a 3-part total problem, and an equation that students could use to solve this problem would be 13, that's the first part, plus 32, that's the second part, plus 40, that's the third part, and then they're putting those parts together. There is irrelevant information in this story. We don't need to know about Jackson. And so students would write this equation here and then solve this equation to answer the word problem correct. Now, for the equation that I showed you on the previous slide, and for this equation here, these are fairly straightforward equations. So here, hopefully we would work with most students and they would see that they have to add 13 plus 32 plus 40 to solve the problem correct. But then we get to problems like this. So the baker has 42 chocolate and strawberry cupcakes. If 26 of the I'm sorry, gosh, I can't talk this morning. If 26 of these cupcakes are chocolate, how many are strawberry? So this is also a total problem. We're given here the total number of cupcakes, and we're given one of the parts, and our job is to figure out the other part. And so here, students would set up an equation most often like the first one, 26 plus question mark equals 40. I wrote 40, it should be 42, sorry. And so this is going to be a much more difficult equation for students to solve. And so that's where this role of equation solving within word problem solving is going to be really important to investigate. Now, some students might be able to start to transition to say like, well, I was given the total amount, 42, and that equals 26 plus question mark. But most of our students will write a pretty standard equation like 26 plus question mark equals 42. They don't always write a non-standard equation, but that is a possibility that they could do. Now, then we look at some problems like this. This is pretty similar to that question that we looked at earlier where the students were comparing math and writing. Here, how many more games did the Bulldogs win than the Cougars? This is a difference problem, and here students could write an equation 7 minus 3 equals question mark. I'm now going to transition to using x as our variable to represent the unknown. And then this is a more complicated difference problem. Here we have 8 more stuffed animals than Kingston. If Kingston has 7 stuffed animals, how many animals does Dion have? So here we're given the difference, which is 8, and we know that Kingston is the lesser amount. And so our job is to figure out the greater amount. And so we would write an equation x minus 7 equals 8 to represent the structure of this word problem. Now, I thought it would be fun to look at the 2 problems we looked at earlier. So for this problem here, this is a total problem. We're given the total and we have to find one of the parts. So students could use an equation 25 plus x equals 96 to represent what's really going on in this story. And then for this one about comparing math to writing, here we would compare 22 minus 13 equals x. You'll notice in Lynn's Pirate Math program and our Pirate Math program, we use X to represent the unknown. That's probably one of the reasons we call it Pirate Math. We use X to represent the unknown, and we talk about X is like your word problem treasure, like on a treasure map where a pirate is searching for X. And students really get into these pirate themed activities that we do in both programs. We'll say like, are you ready to solve word problems? And students, really get into it, and they can earn little pirate prizes, and it's very fun for them. So the work that I want to share with you occurred within the Pirate Math Equation Quest program. And so every day we did 5 activities, very similar to Lynn's Pirate Math. We did some speeded practice in terms of fact knowledge. Here we did this through Math Fact flashcards. And then I'm going to talk to you about Equation Quest. This typically lasted 2 to 5 minutes within a 30-minute lesson. And I'll show you what we worked on in Equation Quest with our students. And then students went into what we called Buccaneer problems. This is where students were setting up and solving the total difference and change problems. And then the 4th activity in each session is that students sorted word problems. So they decided whether word problems were total difference or change problems without solving those problems. And then finally, there was a review at the end called the Jolly Roger Review. You can see this is very pirate themed for the students, and it's really kind of a fun part of the word problem intervention. But I want to focus on Equation Quest. So in Equation Quest, we did several things with the students to really help them understand how do you solve these different types of equations? Because a student can write a beautiful equation, 26 plus x equals 42, but if you don't have the supports to solve that equation, it's not going to help you solve that word problem correctly. And so one of the first things that we did in Equation Quest, and then we did this every day throughout our 51 session intervention, is that students learned about the equal sign. So we talked about the equal sign as an interpretation as the same as. So one of the first things students would do is that they would read different equations, and instead of saying equals, they would say the same as. So here are some of the equations that students would read. So they would say 6 plus 8 is the same as 14. And then for the next one, which is a non-standard equation, the equal sign is not in the position where we would typically expect it to be. They would read this as 11 equals 5 plus 6. So we did a few days of this interpretation of the equal sign. And then every time that students saw the equal sign in Equation Quest or in the rest of the Pirate Math Equation Quest program, they would talk about the equal sign as meaning the same as. And that was important because we did activities with students where they would start to think about that same as a balance between the two sides of the equation. So students did activities with manipulatives. Here's a mat that students would use to balance the two sides of an equation. And we would use cubes or motors or lots of different manipulatives to set up and solve these equations. Notice that some of the equations that students worked on, such as example A, are solved equations. So here we would put 10 items on the left-hand side, and we would say, what happens when we subtract 6 objects? So we would do the subtraction, and so we would have 4 remaining objects on the left side of the equation, and so students would place 4 objects on the right side of the equation so that they could see that 10 minus 6 equals 4, but as you do 10 minus 6, 4 equals 4. So really understanding 4 is the same as 4. And then students would solve equations where they have to figure out a part of the equation. So they would set up 5, they would subtract 2, and then they would figure out what has to be on the other side of the equation so that 5 minus 2 is the same as here, 3. And then, for example, C, this is a non-standard equation. And so we're really testing students' flexibility with understanding that the equal sign in the equation, it doesn't matter where it is, but we're always going to interpret that as the same as. So for this equation, blank is the same as 8 minus 3. Students would set up their manipulatives on the right side of their mat and then balance those two sides. Now, we did a lot of this with this mat and different types of manipulatives. We also brought in balance scales, and we would draw an equal sign in the middle of the balance scale, and students would balance the two sides of that equation. Now, beyond manipulatives, we also used a lot of drawings with the students. So this is one of the pages in the Equation Quest program where students would draw. And typically they would draw circles or squares or triangles or X's, whatever they felt comfortable with drawing. This is an important part of using these multiple representations here, knowing that students might not always have manipulatives with them, but they could draw to set up and solve these different types of equations. So for the example A, students would draw maybe 4 squares, and then they would add 6 circles, and then they would show the 10 on the other side of the equal sign to show that 4 plus 6 is the same as 10. And then for B and C, we're starting to help students solve equations where we aren't just adding, but here we set up 6 on the left-hand side of the equation and 2 on the right side of the equation. And then students would ask themselves, well, how many do I need to draw and add to that 2 so that 6 is the same as 4 plus 2. So lots of manipulative work, lots of drawings to really help students think flexibly about the equal sign and then how to solve these different types of equations. Now, around the 10th day of Pirate Math Equation Quest, we introduced this idea of this unknown. So here in the left, you can see that there's an unknown or variable X, and it's surrounded by all of these numbers. And so in this activity, we're now going to start to teach students to isolate this X. For many of you, you're like, yeah, that's what you do. That's algebraic, right? Remember that we are, I maybe not even said, we were doing this with 3rd grade students, all of whom experienced math difficulty. So introducing this variable to 3rd grade, and in the US, those students are typically 8 to 9 years old, and asking them to isolate this X from all of the other numbers and to do this equation solving. This is a lot of algebraic reasoning that we're introducing to students pretty early on. And as you'll see, the students really get it, just as they really understood these different language constructions that Lynn was talking about. Once we explicitly teach this equation solving, they really run with it. I'll show you a few examples of that on the following slides. But here the idea was that students would separate the X and that could equal all those other numbers. But here we're isolating the X because that's going to be an important part for solving equations. So once we introduced X, then students would work on different equations such as these. Here you can see that the unknown is in different positions in these equations. Some of these equations involve addition, some of these involve subtraction. And I'd like to show you a few examples of how students did this in their work. So here is one of our word problem work examples from the student. Here you can see we have a graph. One of the things that students did is they labeled the graph as soon as they saw a graph, just so that then they have those numbers there and they don't have to kind of go back and see like, oh, how many were in December, how many are in January. If they label those initially, it's going to be really easy to use those numbers once you have to solve them in the problem. And so here they're figuring out the snowy days in December, January, and February. And if you look at the students' work, there's a few interesting things going on here. Students wrote the run strategy on their paper and they wrote it vertically. So they remembered first they run, they read the problem, first they underline the labels, and last they name the problem type. And you can see the students checked that off as they did that. This is a total problem with 3 parts. And so students wrote the P1 plus P2 plus P3 equals T equation. And in here, they placed in the information from the graph to solve this equation. For the total, that's the unknown. So they marked that with an X. And then here there's not a ton of equation solving prowess that you need to solve this, but they did add 6 plus 11 plus 9, and you can see how they're doing their work there. And then they showed that our unknown are X. That means there were 26 snowy days, and they put a label on their word problem work. Now that's fairly straightforward. So I want to show you how students solve some of these equations that were a little bit more difficult. So this question is that there were some jelly donuts and then Steve bought some more. Now there are 18, he bought 3 more. How many donuts are on the plate? So you can see the run strategy is over on the left-hand side. So we've run through the problem and then the student identified this as a change problem. So they wrote the change equation, ST plus C equals E. And then they placed in the information that they knew, and then they marked their unknown. So here the equation that the student set up was x plus 3 equals 18. And if you think about that, that represents exactly what is going on in this story. We don't know how many jelly donuts there were, and then we bought 3 more, and now there's 18. So x plus 3 equals 18. So here, I want to just briefly talk about why the student circled this X. So we circled the X to really focus on the X and to isolate that variable. And then we taught students that if we want to isolate X, we need to remove the number that is with X on that side of the equation. So we worked on some number line activities where if you have positive 3, and if you add 3, and if you subtract 3, you would be at 0. So you can see that students are subtracting 3, but whatever you do to one side of the equal sign, remember that's the same as the other side. So you can see they subtracted from the other side. There is a line that the student drew from the equal sign, so they're trying to balance those two sides of the equation. They have a line in 18 minus 3. We can see that they're separating their 10s and 1s to subtract. And then they subtract 18 minus 3 is 15. So the unknown. Actually, oh my gosh, they solved this problem. No, they did that. Okay, wait. Yes, okay. So that's exactly right. So they solved this problem correct. I was tricking myself when I was looking at that minus sign. X equals 15 donuts. Over on this right-hand side, our tutors would bring in like little fun stickers and stamps. And so you can see that they got like a little good work stamp and they have this C plus there. That's not a grade. That actually shows that this is a change problem with an increase. So the student is making that notation pretty early on in the run strategy to help them solve this problem correct. And then finally, on this problem, this is a total problem here where we have an unknown part and we're given the total. So I won't talk through this one all the way, but the student sets up the equation 19 plus x equals 34. They subtract 19 from both sides to solve for the unknown part, which is 15. And then on this story, which is a different story, this student is now, we're lesson 50, so we're almost at the end of the Pirate Math Equation Quest program. And in this one, the student is not writing a difference equation anymore, and that's fine. Students kind of like fade out of that, but they are writing the equation that represents what's going on in this story. So x minus 33 equals 56. Here, they're going to add 33 to both sides to isolate that x and solve for 89 stamps. They crossed out irrelevant information in 3 years. That D over there, again, not a grade. That means that they're solving this as a difference problem. So why is this important? So pretty similar to Lynn, Lynn did some different mediation models to look at language comprehension. Here we did a sequential mediation model where we looked at equal sign understanding and equation solving, and then that impact on word problem solving. So in this study, we had 304 students, all at 3rd grade and all experiencing difficulty in math. And those students were randomly assigned to one of 3 conditions. The first was Pirate Math Equation Quest, which is what I've been talking about here. The second was Pirate Math alone. So that's Pirate Math without the Equation Quest activities. And then some students were randomly assigned to a business as usual control group where they did not receive tutoring from our research team, but received regular math instruction in the classroom. And so if you'll focus on the orange rectangles here, that kind of shows the significant pathways in this model. So for our Pirate Math Equation Quest students, which is PMEQ, versus students in the BAU, we see a significant path to understanding the equal sign. That's the EQ that you see kind of in that second orange rectangle. So understanding the equal sign as a balance, understanding the equal sign as meaning the same as, we had an assessment that looked at equal sign understanding. And so we saw that that was really important for those Pirate Math Equation Quest students. But that in turn led to improved equation solving. So that this is the OE is an open equations measure where students solved different types of standard and non-standard addition and subtraction equations, such as 2 plus blank equals 5, or blank equals 11 minus 6, or things like that. And so it's this equal sign knowledge that is important for equation solving. And then therefore the pathway from equation solving is significant on the word problem outcome. So we can see that there's this added benefit of doing all of this work around the equal sign and equation solving on word problem solving compared to students who did not participate in Equation Quest, but who did participate in Pirate Math. We do not see that same sequential mediation model at play. And if you'd like to read this paper, it just came out this year. It's Alternative Paths to Improved Word Problem Solving. And I do want to thank the research team that did all of this work, an amazing group of tutors, as well as Lynn, who provided a lot of feedback on Pirate Math Equation Quest as we were developing it and fine-tuning it. And this work was funded by the Institute of Education Sciences. So that's all we have for today. Now we have about 10 minutes for questions. But just to remember, the innovative components that we focused on today was that we don't want to do word problem intervention without a focus on language. And we also don't want to do word problem intervention without a focus on setting up and solving those equations. So I'll stop there. And I just want to thank MCLS for asking Lynn and I to share our work today. So if anyone has any questions, we'd love to talk more about this work. Or there are no questions.
Well, I'll ask a question if I may.
Yeah.
I think this the intervention or interventions, I should say, fit into a sort of generic type of intervention in which you kind of focus on an intermediate level of abstraction in order to get people from the most concrete to the most abstract level. So in this case, the most concrete level being the word problems, the most abstract level being the equations, and the intermediate level being these schemas, such as compare and difference. So I guess any approach of this form is always going to involve some extra work in the sense that you're introduce something that's essentially scaffolding that you eventually don't really need. I think you described that those eventually are sort of faded out.
Mm-hmm.
I wonder if you could speak to sort of under what circumstances it's worthwhile to undertake that kind of extra work, and in what cases it's just going to be unnecessary extra work. Obviously, in this case, it seems to be useful, but can you generalize from that?
Yeah, I'll take a stab at that, and then Lynn, I hope you'll follow up. So the work that Lynn and I are doing is often with students who are experiencing math difficulty. And I think at the beginning of the presentation, you can see that without this type of instruction or without this focus on the schemas, students really have a hard time approaching the word problem and solving the word problem. And so a lot of our work, and Lynn has done this at first, second, and third grade, and I'm now doing this at third grade and fourth grade. And we see for students who are experiencing math difficulty, and most of these students are in the general education math classroom. Rarely do these students have an identified disability, but this work is really important for these students. And in the study that I shared with you, we did that work at third grade. And then we went back and followed those students up in fourth grade about 6 to 12 months later. And we still saw that the students who participated in Pirate Math Equation Quest, while the effect lessened, they were still performing significantly higher than the control group on the word problem outcome. So we saw that the work that we were doing around these schemas had staying power. But when I was working with Lynn at Vanderbilt, Lynn, I'd like you to talk a little bit about our second grade project where we did this with all students, a range of students in the classroom, and how important that was for all students in second grade.
Yeah, so we, in that study, it's a 2014 Journal of Ed Psych study, we looked at the effect of this kind of scaffolding that includes the different levels of support and abstraction that you're referring to with students who, anybody who's in the general education classroom. Students who are at risk got a secondary level of intervention, supplemental to a small group intervention to support them additionally. And in that study, we did not contrast the use, we didn't do it with and without that intermediary level of scaffolding. So everybody got the standard framework. We found that students in the pirate math condition compared to a condition that had similar structure, but focused entirely on computation and calculations, the students benefited from this approach. So it's not that we have a study that actually isolates the effect of having the representation in the form of the number sentence that's expressed in terms of words or symbols for those words. But we, I think, moving immediately to a level of abstraction that's represented with the missing quantity in the placeholder for the schematic, the missing quantity would be extremely difficult for the at-risk learners that we're working with. So we don't have a way to isolate that intermediary level. But if we did such a study, I would guess that students' incoming abilities, cognitive processes, as well as mathematical skill would moderate the need for that additional level. And in fact, many students don't need a lot of structured instruction in word problem solving. They have very strong language skills. They have very strong math skills, understanding, and they can solve word problems with minimal structure from the classroom teacher. But there's a large number of children who do require a lot more structure to be able to succeed. And we see many examples of situations where students have intact number knowledge and computation skill, and yet they can't handle word problems.
Mm-hmm. Yeah. Joanne, good morning. I saw you raised your hand.
Good morning. Amazing presentations. Thanks so much, guys. That was really inspiring. The question that I have isn't really about your research per se, but I guess the question, when I see what the ways that your interventions provide information for kids and train them and so on and so forth, I guess my question is, why is this an intervention as opposed to just a good way to teach kids how to solve word problems? I mean, maybe that's the way you present it when you talk to teachers, but I couldn't help but think, well, this makes complete sense because you're essentially training them how to do the tasks that you want them to do. So could you comment on that?
Yeah, I mean, I think that Sarah and I would, and I readily agree with you that this would be, a really central feature of the regular classroom program. And in the study that Sarah mentioned and that I talked a little bit about, that's the approach that we took. The teachers liked it, the kids liked it, kids learned well, and I think it helps children think about word problems in a way that enhances mathematical understanding generally, which would be a good, question to look at. But we would agree with you. Am I right, Sarah?
So
I agree.
What are
Joanne.
the teachers doing then? What if they're not doing this, which seems perfectly like what they should be doing?
Yeah.
What are they doing?
Well, a lot of so we just did a survey with about 40 teachers in our area about how they teach problem solving. And the number one thing that teachers said that they do is they teach keywords. So we know that they're using really ineffective practices. But I agree with you, Joanne. And I'll give an example. I was working down last Thursday in South Texas with teachers for 6 hours, and I was doing a session on word problem solving. And I wasn't teaching them to do the pirate math intervention, but I said, there's two really important things. And when it comes to problem solving, students need to have an attack strategy, whether that's run or a UPS check or something like that. And then they need to focus on these. And we talk about the 6 schemas across grades K through 8. And so, I'm teaching them here's how to use a graphic organizer and equations to solve these problems. And so I agree with you. And teachers are just eating it up. Like, oh, okay, yeah, because word problem solving as we see it, especially in American textbooks, is just very underdeveloped, if it's developed at all. So I think Lynn and I both totally agree with you that this is a really strong approach for all students. Most often we're doing this as interventions because sometimes I think it's through the funding mechanisms where we're exploring these different options.
Yeah, I think that although this way of thinking about word problems in terms of schemas, it helps any individual, regardless of their age, sort of put a structure to what is often just a sea of word problems.
Yeah.
And I think that part of what we do in mathematics instruction, hopefully, is help students understand the patterns that are available to them. And that has been developed in so many aspects of math in the regular classroom and in the standards, the state standards.
Yeah. But
you don't see any emphasis on that when it comes to word problems. So it's definitely a goal to spread the word to general education.
Thank you so much. I know we're at the top of the hour, so I just wanted to thank Sarah and Lynn for these excellent presentations and this discussion. Just wanted to remind everybody there is no MCLS event next week, but the following Thursday on December 2nd, we will have a symposium on the home math environment in different contexts. So we hope to see you all there. Thanks again to our presenters today.
Thanks,
everybody.